simulated annealing, it is also an example of local search algorithm, but it is you can say the enhancement of the previous algorithm, which is a hill climbing algorithm. Now in a hill climbing algorithm, we have seen that we cannot go downhill, means we have to go up, and when reach the local maxima, we say this is the solution in the hill climbing algorithm. Now this is the first drawback of your hill climbing, like your local maxima, your plateau, means your flat surface or ridge surface. So if you are getting all those things, we are not getting the global maxima. The second is another algorithm, which is a random walk. So if I have given you the options, we randomly walk into the options and we'll try to reach the goal. Now what happened in both the algorithm, the random walk algorithm and the hill climbing algorithm? In the hill climbing algorithm, the cost is less, but you are getting only the maximum local maxima. You are not getting the global maxima. But in the random walk algorithm, moving to the successor, chosen uniformity at random from the set of successor is complete but extremely inefficient. Why? Because we are randomly walking to all the neighbors, and when we reach the goal, we say we reach the goal. So random walk is not based on any value or any, you can say, objective function. Random walk means we are randomly choosing the successor nodes. But if you will mix these two methods, so you will get advantages of both the methods. What is that? The advantage of hill climbing is least cost. Cost is less. Why? Because we are using very less space. If you'll choose the random walk, we may get succeed. We may get global maxima. So both can be added here and make an algorithm which is called simulated annealing. Now, simulated annealing is having two parts. One is simulated, another is annealing. Annealing is a process in metallurgy in which we give the temperature to a metal, and we will give the temperature to the metal up to a peak value so that the metal can take a shape and become harder by cooling it down. So if I want to make a metal harder, means I want to remove the impurity of that particular metal. So I give heat to that particular metal, and slowly I'll make it I'll reduce the temperature slowly so that I can reach one state where my metal will be in a good shape and without the impurity, means it will become hard, right? So that process we'll use in our algorithm also. Now what we do is, in the previous, if you have understood, if my neighbor is not giving me good value than my current value, so I'll not go into that particular neighbor. If my neighbor is giving me good value means in terms of your objective function. If the objective function value is good, I'll go into that particular neighbor, and that neighbor will become my current neighbor, right? Otherwise, I'll not go further. But here, in the case of simulated annealing, I can go further also with some error correction. I'll do some error correction and I can go into further state so that I can reach the global maximum. This is the objective of this function. Now, in this particular simulated annealing algorithm or simulated annealing approach, you have one algorithm here. If you'll see, we have a problem and we have a schedule. Schedule is all about the schedule of the temperature. What should be the temperature value that is there? So let's say if you have started with the 3000 degree Celsius of temperature for melting a particular metal, and then from that 3000 you are going towards your temperature which will give you a best metal. Best metal means less impurity, become harder, right? So that is the schedule in this particular algorithm. We'll map this particular process to our computer terms. So that's why instead of that temperature and all, we say schedule. Now let's say the initial state. Initial state will say it is a current state. Initial state means having the higher temperature, and we'll start with the higher temperature, the maximum, and we'll go up to the minimum, right? So we'll go into one initial state, and that will go from 1 to infinite, means up to this particular loop will go on. So let's talk about this. We have a scheduled a small t, and we'll get the value capital T. If that value capital T is 0, then we'll return whatever is the current state. So this is the termination. This is the termination. The termination is if the T value is 0, means your temperature is 0 degree. So that is your current. Now what we do is a random selection of successor of the current will do. Are you getting it? Means if we have a state, that state has, let's say, 3 neighbors. So what we do, we choose any of the neighbor randomly. And after that, what we do, the current value and the chosen next value randomly that we have chosen will find out the difference between these values. Next value minus current value, it will give you delta E. Now we choose delta E. If the delta E is greater than 0, then what we do, that next node will become the current node. Getting it? You have a node, let's say 3 successors are there. From these 3 successors, we'll choose any of the successor randomly, because we are merging hill climbing and random walk. So we'll choose any of these randomly. After that, what we do, we find out the difference between 2 values, current value and the next value. Okay, so the next value should be higher than the current value. If it is, then that next value will become the current value. If not, what is the else condition? Else condition is we choose this next node as the current node only with probability e to the power of delta E by T. It means that particular value should be in between 0 and 1. There should be no negative value. Then also we choose next as the current. So we have 2 ways to choosing next as a current. In the previous one, we have only one. Like if we have the greater value, we choose the current one in the hill climbing. If we have equal to or less, we'll not choose the next as the current one. But here, we'll choose the next as the current if it has the greater value, because delta E is telling about that. It has the greater value than your current value. That's why these values are positive, and you are getting the next as the current one. And you'll get the next as a current one with this probability also, e to the power of, means exponential to the power of delta E value divided by T, some positive divided by some T. You will get some value which is in between 0 and 1. Then also you can choose next value as the current. So what will happen here in this particular case? In this particular case, what will happen? We are climbing up. We are climbing up. We are climbing up, up. And now we are reaching here. From reaching here, in the hill climbing, this will become my current node. I cannot go further because all the value are flat. But in case of simulated annealing, I have a chance to go further also with with what? E to the power of delta E by T value. Okay. Now, if you see the same algorithm with another way means it's a different way, but it's the same algorithm. Now, if you see this, we choose any initial state to the current state or the current value. We will starting a loop with a temperature, maximum temperature to the minimum temperature. We don't know what is minimum, right? Maybe the 10 degrees Celsius will be minimum. Maybe the 20 degrees Celsius may be minimum. Maybe 0 degrees Celsius will be minimum. So it will be like, we have started with a maximum. Maximum may be 200 degrees Celsius, 300 or 1000 degree or 2000, whatever it is. Some values are there. Now here, E is telling you about the energy. Energy of the current node or the current state will be EC. Okay. The next of the current will be chosen as next. There is a random process of choosing the next, and we'll find out the energy of the next or the value of the next. Now what we do is we do the difference between the next and the current, like in the algorithm that we have seen, and find out delta E. If delta E is greater than 0, we'll choose that particular next node as the current node. Okay. Else, if we have exponential to the power, the exponent to the power of delta E divided by T, if that value, this probability is in between 0 and 1, so we also choose next neighbor as a current neighbor. Getting it? So this is a way where we might get the global maxima. In the previous example, definitely we are not going to the global maxima. Why? Because we are choosing our next neighbor, and there is only one condition, that the objective value of the next neighbor should be more. Here, the same thing is there. The objective value of the next neighbor should be greater, but if it is not greater, we have the probability in this way. If this value is giving you the value which is in between 0 and 1, then definitely we'll choose the next node as the current node. So what will happen in this is we are not going to stop in local maxima. Instead, we have a chance to get the global maxima, right? This is your simulated annealing.